Okay, today we're going to finish up advanced forecasting with Box-Jenkins. And this is way more than you'll need to know for the ISM test. The only thing you need to know for ISM test is that Box-Jenkins uses this ARIMA model. And this guy will go into it on using it as a forecasting method. If you want to use it, you're going to need MiniTab because you can't do this on a spreadsheet. It's about an hour, so let's get going.
No way. Deadline again? Vacation tomorrow. Let's pack. Where's my passport?
Know that information is key for. Hello everyone, this is Matthew Bissens from TrainFirm. So today we will discuss a topic in time series and forecasting named as ARIMA. ARIMA is autoregressive integrated moving average method, which is used for forecasting or predicting the future values of a time series. And we will particularly discuss on how to conduct this analysis and generate forecast using two basic softwares. One is MiniTab, the other one is RStudio. So let's get into the details of this. So as I told you, ARIMA stands for autoregressive integrated moving average. So here, when to use ARIMA is a question which we will need to be very clear with a good reply or a good answer before we start this lecture. So ARIMA is used when there is a strong seasonality or a trend or a both present in your time series data, right? So AR stands for autoregression, where MA is moving average and I stands for integrated, as I told you, right? So the objective of ARIMA is basically to predict the future values of your time series by making your data stationary, right? I've highlighted this group of words, time series, stationary. The reason why I want to emphasize on this, by making your time series stationary, you are trying to identify the various components in your time series using ARIMA, right? You have an AR component, you are an MA component, and you have a differencing component, right? So you are trying to extract these components, right, from the time series data, and after extracting this, you use these components to create forecasts for that very same time series. So to generate the forecast, first you need to make your time series real stationary, right? It is only then possible to extract all the information required to figure out the components of AR, MA, and I from your data series or time series to build a model to create forecasts for future. Okay, so you must be wondering what these words PDQ and AR, I, and MA are. Don't worry. Let's discuss on those topics one by one. So AR stands for autoregressive, which is the number of components in AR is denoted by the letter P. That's what you can see here. So autoregression is a phenomenon which is expected in a time series data. So autoregression means correlation between two data points, right? So in a time series model which is ordered through time, it is expected that the first variable or the first data point may be related to the second data point, and that correlation is strongest when it comes to subsequent points, right? So, or it could have a correlation between the first data point having a correlation between the third data point, the first data point having a correlation between the fourth data point, so on and so forth, right? So the correlation exists because it is timely ordered. So some instances or some events during that time period may influence the next data point in that series because of the impact that event made on that data point, right? This is how correlation gets built, right? So that's called as ARPs, where there is a correlation between data points in time series. So we are trying to learn what is the degree of correlation and where exactly the correlation exists in this time series. Is it between two subsequent data points, or is it from one data point probably to another data point which is 3 time periods ahead to it, whatsoever it is, right? So we'll need to know that information is key for us to create a forecast. The second term is the MA term, what you can see here, which is called as moving average. The components are notated by the letter Q, the small letter Q. So moving average, don't get confused. This is not the moving average, what we discussed in the ratio to moving average. That's different. Here, the term moving average stands for the errors, the correlation between the errors. So AR was talking about the correlation between the data points, where moving errors or moving average is talking about the correlation between the errors. So obviously, as you know, that when you predict, there will be a corresponding actual value also for that prediction, right? So we make some predictions for tomorrow, and then we will observe the performance and we take the actual value. So predicted versus actual. So if I take a difference between the predicted versus actual, I get the error component. So I will have an error component for each and every data point in a time series. So I'm going to study regarding the correlation between these errors, right? How the error 1 is correlated to error t minus 1. How error 1 is correlated to error t is correlated to error t minus 2. The same study is done, and we want to identify what's the level of correlation between data points, if at all there is a correlation which exists, right? And we need the number of where exactly these correlation happens, because is it a first lag correlation or a second lag correlation? Means the first data point is correlated to the second, or first data point is correlated to the third, or vice versa. So we need to know till which point does that correlation exist in this time series data, right? And those many components are to be used in our ARIMA model, right, to create the forecast. The last term is I, which is called as integrated. We are integrating AR and MI. To make the data stationary, we go ahead and take a difference between data points. It could be a first order difference, second order difference. The same way I told you, it could be difference between subsequent data points, or the first data point to the third data point. This is done to make the data stationary, right? So that number of differences we take, we denote it by a letter D. So these 3 basic ingredients are required for me to generate an ARIMA forecast, right? These are the building blocks for my ARIMA forecast, okay? So now we have spoken about the basics of it, and I kept on pressing on one word, stationary data, right? So how do you make the data stationary, right? That's very important for you to understand at this point in time. So as I told you, in order to generate a solid and a reliable forecast, first you need to make, and of course to use ARIMA, you first need to make the data stationary, right? So when you make the data stationary, that means one of the indications to see whether your data is stationary is that it does not have an influence of a trend, it does not have an influence of seasonality. It just flows, and if I try to put an average line, that would be a straight line which can be used as a representative line for the entire time series. So that is where my data is residing somewhere in a stationary way with a constant mean across the time zone. So that's stationary data to me. So how do you get there? When your data is under the influence of trend, seasonality, variance problems, how do you get the data stationary, right? The first one is to get the differencing out of it. We just discussed about the integrated I, which stands for taking the difference to make the data stationary. So you could take a difference between subsequent data points, right? By doing it, right? You're trying to take the difference in case if there is an immediate trend. You're trying to take the difference and put it in the time series chart again, right? So if there is a small positive or a negative trend in the time series data, if you are taking the differences, that means you are trying to reduce that magnitude and trying to take away or remove the trend or a seasonality component from your data set, which the resultant may give you a stationary data, right? So that's one way of looking at it. You could take a first order difference or a second order difference. The first order difference is between two subsequent data points. That's the first order difference. Second order difference is where you're taking the second order difference of those subsequent points. So it keep continuing till the data is stationary. Generally, we don't go beyond second order differencing. So that's the rule of thumb. And if your data is not stationary, even by doing differencing, there are a few other techniques what we can use. The second is transformation. This technique is used typically when the variance is not stabilized in a data point. That means you see seasonality, but the magnitude of that seasonality keeps increasing or decreasing as when you move through your time series. So that means it's a multiplicative effect. That means the variance is not constant across all the seasonal periods. Here is when I will go ahead and take the logarithm of the original data series to kill this variance or in the different variance in different seasonal periods. So if I take the logarithm, I will be able to reduce the variance of the seasonality and try to make it as stationary as possible, right? So that's the second method of transformation. The third method is seasonal differencing, where if I've got a yearly data and if I prove that I've got a 12-month seasonality, I will go ahead and take the difference between the first data point and the 12th data point, which is the lag of 12, right? So clearly I do this to get rid of the seasonality from the data, right? If I take the difference, I'm going to get rid of the seasonality component. I'm just going to take the difference of it and just move along, right? So from a non-stationary data, it becomes a stationary data because the variance is something what I'm trying to knock out from the time series. So that's seasonal differencing. So it could be a 12 lag in case of there is a 12-month seasonality and it's monthly data available, or it could be a four lag, 4 quarters data, right? In case of 1 year is being represented by 4 quarters, then I can go ahead with four lags to the order of 4 to get the seasonality out, or any sort of a pattern out of the data and to make the data stationary, right? Still, if it is not working, you can go ahead. Once you create the logarithm, you can try to differentiate right, by using a first order difference on the log data, right? Again, apply differentiation on top of it, and you will get to see the data may get stationary. So these are the 4 techniques what generally we use to get the data to a stationary point. So as a rule of thumb, when the properties of a time series does not depend on time, that means your trend is a property which depends on time, right? So as time moves on, either it could be an uptrend or a lower trend, right? And seasonalities, again, it's a property of the time. So if there are no such properties which are dependent on time, that's when I'll say that my time series is a stationary data, right? But however, there could be cyclical behavior in the data. There could be no trend, no seasonality, but the long cycles happen to be there. So that means if there are cycles in the data and with no trend and seasonality visible, I can still consider that data as stationary, because if I put a mean line, that mean line is going to be a straight line across time. So that's where I have stationary data in my hand. Okay. So once you have a data set, right, and you're convinced that yes, of course, I want to go ahead and build an ARIMA model. These are the steps or sequence of events you will go through to get a good forecast for you. So first is to business analyze the data, which I've shown here. Before getting into details, statistics, number crunching, we're going to go and talk to the real process owners, to the SMEs, to the business analysts, how this business works, right? We're going to get a first-hand information from them. What kind of seasonality, what kind of cyclical behavior, what kind of a trend do we expect in this data? So we're going to make a note of all of those things. This is the single source of truth to get to know the real process. So data may be telling you the truth, may not be telling you the truth. You never know. If there is a problem with the data, you could see different patterns and different behaviors in the data. So for you to corroborate, right, you certainly will need this piece of information from the horse's mouth. And then is when you will definitely go ahead and start analyzing the data, right? You create or you plot a time series and check for if there is a trend component, a seasonality component, or the data, whether the data is stationary or not, right? Is the data under an attack of outliers? Are the variance constant across time periods, or you have a multiplicative model and an additive model? So a lot of information comes through basic data analysis once you plot the time series chart. And then the third task to you is to make the data stationary. So either by differencing or by taking the logarithm or taking the seasonal differences or by taking the differences of the log data, eventually you're going to make your data stationary, right? Only then you can proceed with your ARIMA, right? Once you declare that we have made the data stationary, we will not be able to go ahead and use ARIMA. So that's the bottom line. Getting the data stationary is key to ARIMA. So we got to keep that in mind. Okay, so I'm going to take a quick example here and show you how to build an ARIMA model, right? So for that, I would want to take your attention to this case study of tractor sales for 12 years. So tractors, the ones what we use generally to plow fields, right? So I've collected the data for 12 years between a data period of 2003 and 2014, and I've got monthly tractor sales available. And I really want to go ahead and build an ARIMA model there, right? So even before I could start off any analysis, I would go ahead and do a discussion with the business owners to understand what has been my business trends, what's been my business cycles, is there a seasonality in the data, so on and so forth. And I gather as much as information from them, right, before I go ahead and start, right? So the first thing is that business discussion. So obviously from that business discussion, you will by default understand that yes, there is a seasonality and my tractor sales peaks when I'm closing or when I'm probably approaching my peak of my monsoon, because I do plowing of my fields during June, July, August times, or maybe I start from late April where I get the early showers. Once the mud is smooth, I go ahead and plow it and sow my seeds so that the seeds get deep rooted and then I get a good yield for that particular year. And then I really don't buy many of the tractors post August because probably monsoon is over, and that's where I take maximum advantage. If the showers are getting shifted by a couple of months, also my sales will have probably an impact. So that's when during the first showers when the people will get into the dealership and then buy their tractors, because if you buy tractors in any other period, it's going to be useless, right? It's going to remain in your garage. So that's the business insight you will get, and then of course you will get your data and you plot a time series. So this is what I've plotted. You could either do it in an Excel or it could be in MiniTab or in R software, right? So for simplicity, let me open MiniTab for you, right? So let's go ahead and see how this is getting worked in the MiniTab, right? Okay, so I'm gonna open. All right, so I have got these data prefets. Disregard anything what you see after this. This is the year data, yearly data, and this is the number of tractors sold, right? So what I'm going to do is first to create time series plot for this, right? To ensure that we have the right amount of information to analyze the data. So let's do a quick time series plot for this. How do I do it? I just go to my MiniTab, go to Stat. I'm going to click here, right? Just bear with me for a minute. Yes, I'm going to click on Stat on top of the toolbar and then go to time series and time series plots. Just bear with me for a minute. I'm going to show that on the screen right away. Time series plot. Yes, there you go. So I clicked on Stat, I clicked on time series, and I'm getting a window like this, right? So I'm going to do a simple time series. Okay, right? So such a window has already come, right? So the first task is to get my tractor sold data here, and then the time scale. I'm going to use an index stamp, right? The month and a year, and click on OK. And OK, so this is going to generate a time series data for me, right? So this is how we do this in MiniTab, right? So I'm gonna show you that on the screen, the final time series plot. Okay. So what you see on the screen today is this time series plot, which we have built in MiniTab. So obviously, I see there's something peaking up between the April, May, June, July, August types, right? And then it falls down and picks up, and obviously the variance is not constant. The seasonality component does not have a constant variance. It keeps changing, and I've got a strong trend pattern as well, right? So this is so we're very clear that the data is not stationary now, and there's a lot of information in the data which we need to extract out. In order to do that, we have to ensure that we have picked up we have made the data stationary. That's very, very important. That's key to us, right? To make the data stationary and then start extracting the AR components, MA components, and the I components from the data. So first task is to get the data stationary now. So how do we do that? We can do that in MiniTab, right? So let me quickly show you how to work this out in MiniTab. Just bear with me for a minute. Okay, so I'm going to go back to my screen with the data. You all can see that now. Okay, so first step is to get, I'm gonna disregard all those things which you don't need now. So as we had discussed, the first step is to get the variance under control. So I'm going to take the logarithm of it. I hope you can see my data screen. Yes. So I'll go to calculator, right? On the top toolbar, I've got something called a CALC, and within CALC, I've got something called as calculator. So I click on calculator. So let me show that to you how the calculator looks like. Here we go. So this is the calculator, right? So you can see the calculator. So in the calculator, I'm gonna tell the calculator where to store the results. So I'll go ahead and tell him to store it in C3, column C3, okay? And then what's the expression? I want to create the log to the base 10 for the tractor sales. So I'm going to take log to the base of 10. The number which I need is the number of tractors sold, and I'm going to assign a formula so that it gets applied to all the cells in the row, okay? So I'm click OK. So that's going to give me the results. Let me show you. Yes. So I applied that calculator, and then the MiniTab throws out this result for me. So now my task is to analyze this log data and see whether my data has become stationary from a variance point of view, right? So I'm just going to go ahead and check it once again. Go to time series plot. I'm going to show you that on the screen. So I'll go to time series plot. Okay, and then click on simple, click OK. And then I'm going to get the log 10 here, and the timestamp will remain the same. Click on OK. Yes. So what you can see on the screen right now is the resultant of my yes, what you can see on my screen right now is the resultant of my stationarized data. I see that the variance has been normalized, and I really don't have variance in the seasonality pattern. It's a constant variance, a constant. But still, I can see that there is a strong influence of variance plus trend. Sorry, strong influence of seasonality plus trend in the data set. So I have to basically make the data stationary. Only from a stationary data will I be able to extract maximum information. So now I have extracted the information and I've got to a stage where my variance problem has been solved. Now I just want to have this data settle down with a constant mean. So my task, one of the things what I can do, we did discuss, is to take the differences of this, right? So let's go ahead and see in how we take the differences of this in MiniTab. Okay, so now I'm going to take the difference of the log. So I'm creating a column called as difference. So how do I take the difference? It's easy in MiniTab. You again go to stat and then go to time series. And there is something called as differences. So I'm going to show the video on your screen how the differences have come. So in MiniTab, there is something called as differences, and this is how it comes. You go to stat, go to time series, and you pick up differences, and this window is going to come. So what are we going to do with this window? With this window, we're going to take the series as locked in. This is already logged, and I want to store the data in C4, and the lag is 1. Subsequent data points, difference between subsequent data points. I'm going to click OK. So this is going to store the difference data for me. So obviously the first data point will be missing because this I don't have a reading before this, right? So because of that, so let me show you the screen here. Yes, there you go. So MiniTab has already given me the difference data. So this data point will be missing because of the fact that I don't have a previous data point, so I cannot take the difference. But from here I can get the data points because I take the difference of between these two, take the difference between these two, take the difference between these two, and I get it recorded. So that's I'm expecting the data to be stationary by doing this. So how do we check it? We go to again stat, go to time series plot, and I'm going to show that on your screen right now. Time series MiniTabs, time series plot. Okay, and you're going to go ahead and click on OK here, right? And then take the difference data, right? And then the time series timestamp will remain the same, month to year. This will be the timestamp we're using, stamp, and brought the data right here, and click on OK. Boom. Look at it. So my previous data, which was showing variance and seasonality and trend, is no more existing now, right? So I killed the trend, and now also my seasonality is out of the window, right? Mostly out of the window. I don't see a strong pattern whatsoever, right? So what do I do here? In this case, I kind of call this data as stationary, right? So we have enough proof to show that my data is stationary. You can do this in two ways, right? You can easily create a box plot and break it into number of years. 12 box plots will be there, and see whether their means are equal or not. So you can even do an ANOVA and see whether the means are constant or not. If your test turns out to be favorable to your null hypothesis, then that means your data is stationary, and you can go ahead and start doing your ARIMA analysis, right? So let me show that on your screen as well. What was the time series plot? Yes. So This is what I was talking about. Sorry, your window went blank. So this is the time series for the difference data. We see that the data is kind of settled and it is stationary at this point in time. So what I was talking about is you can use these data points and create some box plots by grouping the data because you've got 12 years of data. So you can club all months data into one group for that particular year and just try to run the box plots. Just do a quick ANOVA, you will get to see that. And that's exactly what you see here. We were discussing about these charts we have already created, right? We stabilized, we took the logarithm, right? And then we found that, the variance problem has been settled, but a strong trend in the seasonality lies in the data. So we go ahead and did these differencing and we got this data. We saw that in MiniTab now, isn't it? Right? Yes. And then, as I told you, I grouped 12 data points into one and called it as 2003, and I created a box plot for it and put the means line. I see that, the means line's kind of hovering in the center, kind of a straight line, which I'm assuming I can go ahead and do an ANOVA on this, taking 12 levels of data and prove that whether my means are equal or not. So if it turn out to be with the result that the means are equal, that means your data is stationary. Go ahead and do it, right? Okay, so in the next step, what do we do is to extract those AR, MA and I components. So I component has already been extracted. We know we took the first differencing. So the I component is present in the ARIMA model. It's going to be an integrated model. Now we need to identify what is the AR component and what is the MA component out of these graphs. So there is a tool or a technique what we generally use to plot the ACF and the PACF chart. So ACF and PACF charts are going to autocorrelation function and partial autocorrelation function. This is going to give you a good understanding in terms of how to read out or how to extract these components from the time series. So let's go ahead and do that in Excel. In MiniTab, how to do a PACF chart, right? So it's very important that I go back to my MiniTab basic screens. Hope you can see that. Okay, so now that I have got my difference data, I need to extract the components from this difference data. So how do I do that? Very simple. I go to again stat, I go to time series, and there is something called as an autocorrelation, right? So I click on autocorrelation and there is a tab which is going to pop out. So let me show you what is the autocorrelation tab looks like. So this is the autocorrelation tab, what you can see on my screen, right? So in this screen, what I'm going to do is I'm going to take the series as difference data from C4. That's my series, and number of lags. If you want, you can put the number of lags what you are interested in, or you can put default number of lags. You can ask MiniTab to take the default number of lags, and then store ACF, T statistics, and box Q statistics. Okay, so I'm going to click on OK.
Meet your next pillow. Why do we make our pillow in the shape of a cube? I'll tell you.
So you will get to see this graph popping off. Two things will come. Right. I hope you can see this. Right. So one of the key things what you need to look at in this output is that, yes, I've got an ACF, I've got a T stat, and then I've got the chi-square values, the LBQ values in here. I'm going to explain to you all of these things in a jiffy. So let me see what is there in this graph. So this is called as an autocorrelation function or an ACF plot, right? So this red line is the significant line, right? If any tall bars of the blue bars goes beyond this range, that means there is a significant correlation with these lags. So how do we read this chart? So I've got data till the 40th lag of 36 lags. So first data point, the correlation between the subsequent data points is the first lag correlation or the first lag second lag is between the first and the second, third lag is between the first and the third, right? So I have individually studied the correlations between these data points and I've plotted in this ACF diagram. So I see that, there are instances, I mean, the sixth lag is going beyond and have a significant correlation there of minus 7.6, right? Minus is a negative correlation between my first data point and the sixth data point, right? And then I see a very strong correlation at the 12th data point. You need to remember this had a strong 12-month seasonality, and that is the reason why I see that, these lags at 12, 24, and 36 are significant because of the seasonality, right? So the data points are not random in the ACF. It gives you a lot of confidence that yes, there is a lot of seasonal information lying in this, or autocorrelation lying in this data point, which can be extracted, and we can amount for the AR and MA components from this data point. Okay, so here one more thing what you really need to do is, this is the autocorrelation, and the next you need to create the partial autocorrelation function as well. So go to stat again, time series. There is something called as partial autocorrelation. I hope that you can see my partial autocorrelation screen now. Go to stat, time series, partial autocorrelation. There you go. This is what it is, a window what you would be able to see, the partial correlation. So in partial correlation, again, I'm going to take the differential data as my series, number of defaults, store T statistics in PSCF, and I'm going to click OK. So this is going to throw out a partial correlation chart for me now. Okay. So I hope that you can see my screen. Yes, partial correlation. So partial correlation, the difference between these two it's very important that you understand these two graphs very, very clearly. I hope that you can see this. Right. So autocorrelation talks about the correlation between the data points, right? The subsequent data points, the first data point, the second data point, first data point, third data point, first data point, the fourth data point. So in autocorrelation, we consider the direct impact of the correlation between the first data point and the third data point, but there are indirect impacts also. When you are studying between first and the third, there is an indirect impact or an effect which the second is generating on the first as well, right? So that's called as an indirect. So when you are talking about autocorrelation or in an ACF chart, although we are talking about the third lag, that third lag will contain the direct and the indirect contribution. So that's exactly what you will see here in this chart. But whereas partial autocorrelation, only the direct impact or the direct effects between the data points are studied. The other things are disregarded. So for instance, if I'm taking a lag of 4, then my first data point is the correlation between the first data point and the fourth data point. I will strictly study only these correlation between the first and the fourth. The indirect correlation of the first on second, third and first, and third and fourth, and second and third, I'm not studying. I'm disregarding, I'm removing it out, and then partially studying only the impact between first and fourth. And these two charts are really important and critical for you to decide on the next steps. So I'll give you some thumb of rule, right? So how to understand that a particular chart is representing something or not. So in an autocorrelation chart, right, you need to typically look at that, if the chart is like this, the first lag is the most powerful, and then it has a gradual decrease and it cuts over from the significant zone and approaches 0. That means a gradual decrease, where in this slide or on the graph, what you see on your screen, the behavior is not existing. If such a behavior is existing, that means there is a gradual decrease in significance level. As the lag increases, my correlation strength, the correlation coefficient is also decreasing. That means the degree of correlation is also decreasing, and it diminishes. And in the contrary, for the same data point, right, if you can see in the partial correlation, instead of a gradual decrease like this, there is an abrupt end. Say maybe after one or two lags, all the other lags are going insignificant. That's going to be under the blue red line. That means there is a strong AR function. The process is an AR function, and the MA component is not there. And the number of lags to be considered for an AR is determined by looking at how many significant bars are there. Like for instance, after the second bar in the MA process, after the first bar, all the other bars are going down. That means it's a first order AR process, right? There is no MA component. So in the contrary, right, if you really look at your autocorrelation, if this does not gradually decrease, the way I explained to you PACF, it is having an abrupt end after one or two lags. All of these things are going to go insignificant under the red line, and there is nothing which is beyond the red in the remaining lags. And your PACF graph, your PACF is showing a constant decrease the way we discussed in the ACF, that is decreasing like this after a few significant lags. Everything is going under the significant and slowly approaching zero. That means there is an MA process, right? There is no AR component. There's only an MA component available, and you got to go look at your ACF and PACF and see where the drop happens. And that would be the number of lags you would need to consider as a MA component in your ARIMA model, right? So this is the rule of thumb. You need to look at the way the charts are behaving and how many lags are significant, and those many lags are basically your building components for your. So if it is an ARIMA model, AR model, you're going to look at for that pattern, and then how many lags are significant. You're going to take that number 2, 3, 4, 1, 2, and just put there that it is an AR order of 1. Right? And obviously in this case we have taken the differencing, so differencing, first level differencing, so it's 1. And then moving average, if there is a moving average, to what degree or to what lags the correlation is significant, you need to look at this graph, and if it's a first lag, again it goes to 1. So in this case I see that it is not an AR process. It looks like it is MA process for me, because AR in AR I see that there are no gradual decrease. It's an abrupt change, and I only see seasonality in here. And in my PACF, right, the partial local correlation, I really don't see any major lags, but this correlation settles down and approaches zero as we move along. So I can assume that it may be an MA process without an AR component to it. And the lag is significant only at the first order, right? So I may take that as a first order MA process with differencing of 1, right? So my model could be a 0 for AR, 1 for integrated, and then 1 for moving edge. So it could be a 0, 1, 1. Since there is a seasonality, there's a seasonal ARIMA, PDQ gets replicated, so 0, 1, 1, 0, 1, 1 with a seasonality at 12 months could be my model to be used, right? So that's exactly what I want to show you in the PowerPoint. Let's switch over to the PowerPoint. Okay, so we, as a rule of thumb, I just discussed and I just explained to you. So taking above clues, we see that there are no AR components, only one MA component and one integrated component. So PDQ, so the values of P is become 0 because there is no AR component in there. My differencing, I've taken first level differencing. If I had taken second level of differencing instead of 1, I could have put 2 here. So in this case, we have taken the first level of differencing, and the MA component, I could see that there is only 1 because after the first lag, all of the other things are getting insignificant because the subsequent lags are just because of the seasonality element, right? So this is the non-seasonal part of your ARIMA model, and this gets your seasonal part. So in the seasonal part, again, I've taken one difference to get the seasonality of the radar, and it is definitely an MA process, right? With a significant lag of the first level only. If the tall bars were getting cut after the second lag, that means there is a significance till the second lag or the second order correlation also exists. This could have become, instead of 1 I would have written 2 here. So this becomes my model with a strong seasonality of 12-month seasonality, right? So this gets tricky sometimes. It's not very easy to decipher this. So I can also show in the second part of this video how to use R to identify such a behavior, right? And to get the right model to be used for ARIMA forecasting. But for now, I've shown you how to do this in MiniTab already, right? You go to stat, time series, make your log data, right? By go to calculator, taking the logarithm, and then how to forecast now in MiniTab is very important, right? So I go back to MiniTab. I hope that you can see my MiniTab screen now. So yes, there's a MiniTab screen. So the next thing is to generate forecast, because I've already identified the AR, PQ and PDQ models, the components. So I'm going to go to stat, time series, ARIMA, right? I'm not sure whether you can see my screen so far. Just give me a minute. Yes, so.
Are you struggling in calculus? Having a hard time understanding your instructor? Do you wish there was a better way?
So when I go click, I'm going to get this window, right? So in this window, it's very important that I feed the log10 series, which has my trend component and my seasonal component, right? Both the components are present in this data series. By taking the differencing, I've killed all these things. So I'm going to take that log10 series, and yes, there is a seasonality of 12. I'm telling MiniTab, yes, you got to check for the seasonality of the 12-month. And the non-seasonal component, obviously, so log 10, right? So it's 0 autoregressive. There is no AR component in there. So yes, I've taken a 1 level difference. And moving average, yes, I'm expecting it to be 1. For the seasonal bit, this is for the non-seasonal bit. And for the seasonal bit, again, there is no AR component in there. Of course, I've taken 1 difference to bring down the seasonality. You got to take 1 difference to bring down the seasonality. And the moving average, I see that is about 1, right? I could see that in the PACF chart. That's 1. So include a constant term. It's like regression. It's again, right? What's a constant? When your y value, when your x value approaches 0, what could be your corresponding y value? So that's the constant. So I'm going to include that constant term, and I got to generate around 36 forecast points, or I want to forecast for next 36 months, and the origin is 144. I'm asking MiniTab 2 things to store this data. Say the forecast I want to store in C10 or say C11. Upper limit I want to store in the column C10, or maybe to be on the safer side C15, and then C14, so I don't want to overwrite anything, and upper limit C16. Okay, and then click OK. Okay. So before we get there, I hope you could see. 1 second, let me show you that how we did it. Stat, time series, ARIMA, right? I hope that you could follow till there. MiniTab. Stat, time series, ARIMA. Okay, so It's times ARIMA. You've got it, and you put the log 10. And now we're going to click on the forecast, right? What happens when you click on the forecast? I just want to show you that window before we move on. So I've clicked on forecast. So when I click on forecast, there's such a window happens. So I need lead means how many forecast points I need. I need 36 months forecast. Origin is 144. I've got 12 years of data, 144 data points are there. So I want to start from 144 data point, and I want to store the forecast in column C15 of MiniTab, lower limit, confidence limit, C14, and upper confidence limit. And I'm going to go ahead and click on OK, right? So when I click OK, that's when this window comes, and then again I'm going to click OK here. So when I click OK, a new window has popped up. Let me show you the windows. Okay, a couple of videos have popped up here. So let's go one by one. Right, this is the time series plot. I hope that you are able to see this time series plot. Yes. So it has generated the 36 months forecast. You wanted from 144. So it has started from 144, right? It has generated 36 months of data for you, right? So here, the forecast is ready. And then two things you need to validate here is the ACF of the residuals. So this is the residuals. So technically, there should not be any tall bars or any more information left out in this, because you've taken the residuals and then you're trying to plot the ACF. And similarly, you get to see the PACF as well. So when you see PACF, again, there are no significant things. So how to conclude? We have extracted maximum information, and there is no more information lying in this data set anymore. You have extracted maximum. You have used the PDQ model, ARIMA model. You have asked MiniTab to forecast that. And then now here you have the forecast, which is already seen that. So one thing which you have to keep in mind is to always go to your session window. So let me show you the session window. This is the result, right? These are the key results of your ARIMA model. So what you need to see here is that, or probably I can, so this is how we get the session window. So let's go back to our PowerPoint. In PowerPoint, I've tried to explain it very clearly. So this is what you will look at for in the session window in MiniTab. MiniTab does iterations, multiple iterations, till they get to the minimum sum of square errors. That's what SSC sum of square errors. It is minimized. It started from round 2 and found the parameters what you really need to use for the ARIMA forecasting, right? So that's what is recorded here. The moving average 1. The coefficient you be used is 0.3996, which is approximated to 4, and then 0.61 is the estimate well coefficient, and the constant value is going to be 0.000836. This is the constant we have included, and these are basically my MA component, and I don't have an AR component, so these are the constants what I will be using for my seasonality, and this is for the non-seasonal data, right? And using these parameters, I'm going to create the equation and then create the forecast accordingly. And one more thing, what you really need to look at is this. This SSC is something what you will need to say how accurate is your data. So obviously, when you look at this slide alone and look at one single SSC value, you wouldn't be able to assess. So if you're creating multiple models, these values can get compared to the other models, and whichever has got the minimum SSC will be chosen as the preferred one. So we've just done one here. So I'm just telling you, this is the value which you really need to look at to confirm whether your model is a reliable model or not. And finally, this is a chi-square test done on the residuals, right? It's a hypothesis test. The null hypothesis says that, it's a good fit, what you have created, and the alternate hypothesis, it's not a good fit. So obviously, when the p-values are significant is when you will have to reject a null hypothesis and say that it is not a good fit. So here at a 95% interval, 95% confidence, we see that it's 0.39. So it's the 39% risk when you are rejecting null hypothesis. I will not reject my null hypothesis. So that means this is a good fit. The goodness of fit is fine. The fit what I've made from a residual point of view, and we did it in the PACF, and we did see that in PACF and SCF, that there are no more information lying. So that means a good fit for me. So all the lags 12, 24, 36, and 48, the residuals are not significant, and it's a good model to be used, right? So this is how you do in ARIMA in MiniTab. I'm going to post another video soon how to do the entire steps what we discussed in R. It's going to be a shorter video. It's going to be easier for you as well. And I hope that you enjoyed the video, and I hope that you understood how to apply ARIMA and how to do ARIMA using MiniTab. In case if you've got any questions, please feel free to drop an email at info@trainfirm.com. I shall clear your doubts, and we can also get onto a WebEx session if required if you have further doubts. So happy learning to you all. Just keep using these techniques in your projects and your area of work, and let's get to the next level. Thank you so much for watching the video.
Okay, so that is the Box-Jenkins method. Again, all you need to remember is it uses this ARIMA model.